Our next topic is going to be Newton's method. It's another open domain method, meaning that we do not need to bracket the root. And in fact, with Newton's method, we will be only using one initial guess. And Newton's method is one of the most popular nonlinear solvers out there. And we're going to see how we're going to extend it to solving systems of nonlinear equations. The way to derive Newton's method, one of the ways at least to derive it, is to start by taking a function, f of x, arbitrary function, and writing the full Taylor series around some point x naught. We saw how to do this in finite differencing a few lectures ago. That being said, f of x is f of x naught plus x minus x naught f prime of x naught, etc., etc. Now, we're going to treat x naught as an initial guess later, but first let's see what we can do with this. Now, we're going to truncate this series by taking only the first two terms. It's just a legitimate approximation. We know that we can do this. Now, we're going to ask the question, what if we set f of x equal to 0? And then trying to find x. So think of it this way. We are always after finding a recipe such that starting with an initial guess, apply this recipe over and over again to improve this guess until we reach the root. Now the root over here is dictated by f of x equal 0. And right now we have some formula that we can probably use to develop a recurrence relation. So go ahead and try to do that. If you treat x naught as a guess for the root of f of x equals 0, use this two-term Taylor series to develop a formula to improve that guess. Pause the video, take a couple of minutes, and see what you can come up with. Okay, so we simply take that formula, the two-term Taylor series expansion, and set f of x equals 0. That's what we want. We want f of x equal to 0. That's where our root lies, right? So that gives us 0 is approximately equal to f of x naught plus x minus x naught f prime of x naught. Now we know x naught, we know f prime of x naught. What we don't know is x. So simply we solve for x, and that gives us x equal x naught plus of f of x naught over f prime of x naught, and that is Newton's method. So if you think of this formula is simply one step in an improvement of x0. Right? Now we can use that new x and apply the same formula over and over again until we reach the root. And lo and behold, this method does converge most of the time. And we can develop an algorithm given x0, f of x. And if you know f of x, you know f prime of x. Then you first calculate f of x naught and f prime of x naught. Calculate a new guess for the root, call that x1 equal x naught minus f of x0 over f prime of x0, and then check for convergence. If f of x1 is less than a certain tolerance, stop. Otherwise, treat this new x1 value as your x0, as your initial guess, and then repeat and improve the guess. And this is easily implemented in a Python code, and I'm giving you here the code for Newton's method. And the arguments for this function for this routine called Newton, we need the function f, we need its derivative, we need an initial guess x0, and we need a tolerance. Now note, compared to the previous routines for the secant method and others, I also passed a max iteration. That's completely legitimate. In this case, I'm going to hard code the maximum number of iterations so that we don't go overboard. Typically, usually if you don't converge within 10-20 iterations, you need to find some other method, because these nonlinear solvers, when used in very expensive scientific computing methods like computational fluid dynamics, you can't afford to do more than 10 iterations every time you use this, because this routine is going to be called millions and millions of times. Anyway, the rest is sort of obvious. We know x0, we simply calculate x1 as being x0 minus f of x0 over df at x0. And note, df is just another Python routine that computes the derivative at x0. And then that gives you the solution, a routine for Newton's method. Your activity now, coding activity 4, is to use Newton's method to find the drag coefficient, again for our famous parachutist. You should be able to do this with your Jupyter notebook that you downloaded earlier. So let's go ahead and open that. parachutist example. Okay, I'm gonna drag this over here and increase the font size a little bit. So activity 4, Newton's method with analytical derivative. Now, if you don't remember, this was the parachutist in free fall. You probably have to execute all of these functions again, all of these cells. This is the residual function given m0, t0, and u0. Those m0, m0, t0, and u0, they're set as global arguments, so you change them anywhere, they're going to change in this function. Okay, and then we plot this for a parachutist of 70 kilograms and reaching a velocity of 40 meters per second. We know there's a root around 15 over here. We had used all other methods previously, bisection and secant and method of false position. Now we're going to come to Newton's method. So we're going to execute this routine over here. We're just going to define it. Next, we need to obviously define the derivative for the residual function. And I went ahead and calculated that for you. You can do this by hand or run it through a symbolic manipulation software. It's kind of annoying, and that's the point here. We're going to try to address that in a second. However, this is the derivative. So to program the derivative so that we can pass it to the Newton method, we simply define another function called df for derivative, or df by dc. And in this case, note that we're differentiating with respect to the only unknown here, which is c, because we're trying to find the root. We're trying to find c that makes this equation, that makes the residual function equal to 0, given m, g, t, and u. Okay, so this is what you get. You just simply define this function and return its value, and you set u0 equal 40 meters per second, and you call Newton's method. What we need is the function f, or the residual function, its derivative, and an x0 initial guess. So we're going to start maybe at 10, and a tolerance 1e to the minus 5, and bam, we get there. So let's see if we can do this with another initial guess, maybe 40. Again, it works. I recall with the secant method we had problems when we were trying to do initial guesses between 40 and 80. However, this works pretty well over here because we're taking the exact derivative at that point. It's going to get us, the derivative is not really 0, so it's going to get us to the right point correctly. And we can do this for 10 meters per second. And we expected the drag coefficient to be much higher in this case because we're slowing down the parachutist significantly. Okay, let's go back to our slides. Now, there's a geometric interpretation for Newton's method. If you're confused about the Taylor series, if you don't like that derivation, how we truncated things, we can derive the Newton's method with using geometric arguments. And you will see that this is going to be a variation of the secant method. In other words, we're going to apply the same methodology we applied with the secant method, but instead of taking 2 points A and B as our initial guesses, we're going to shrink those points, bring them closer and closer and closer to each other until they become 1 point. And if you remember with the secant method, we used 2 points to define those 2 points to draw, and we drew a line between those 2 points. Now, if we shrink both points together, that line is going to become the derivative. Okay, and this is exactly Newton's method. So let's see how this works. First, we start with an arbitrary guess value for x0. Let's say this x0 equal 9 in this case. And remember that we know f prime at x0. So in principle, well, in reality, we can draw a straight line that is tangent at point x0. And where that line intersects the x-axis, we're going to say that this is going to be our approximation for the root. Now, the equation for this line is given by x0 plus x minus x0 times f prime of x0. So that's another version of writing ax plus b for the formula of the line. But here we know x0, we know f prime of x0. And now your question is, using this formula, solve for x1, find the updated guess for the root. So we started with x0. We want to develop a formula to improve that guess x0. We'll call that x1. So go ahead, pause the video here, take a couple of minutes, and try to solve this equation to find x1. Okay. So x1 is the point where this straight line intersects the x-axis. In other words, where that line is equal to 0. So all we have to do is say y at x1 equal to 0. And therefore, we get x0 plus x1 minus x0, we're just simply substituting x1 over here, times f prime of x0 equals 0, and then we solve for x1, and that gives us Newton's method. So this is the geometric interpretation of Newton's method. It simplifies the secant method. With the secant method, we had to use 2 points to define these lines. Over here, we only have to use 1 point, and we, instead of using the line connecting the 2 points, we use the line tangent to the curve at that point. Now, in general, we write Newton's method as an iterative procedure rather than x1, x0. We just say xk plus 1, or the new iterate, is equal to the old iterate xk minus f at xk over f prime at xk. Just simply putting it out there because we're going to be using this form as we go further. Okay, so now you notice that when we ran Newton's method on the parachutist, it was kind of annoying and cumbersome to write down the derivative of the annoying residual function for the parachutist in free fall. So can we do something else to this derivative? And now I'm asking you, based on your knowledge of numerical methods so far, can you propose a few ways to numerically estimate the derivative in Newton's method? So what I'm asking you here is, if you only know f of x, okay, can you estimate f prime of x without calculating it analytically, rather numerically? So pause the video here, take a couple of minutes, and try to come up with a few ideas. Okay, the answer is obviously to use finite difference methods, the chapter that we just finished before hitting nonlinear solvers. And we had looked at several approximations for the first derivative, the first one being a forward difference formula, fx plus delta minus f of x over delta, and we said that was a first order approximation, so we say plus order delta. So that's the definition of the derivative that you've learned, rise over run, essentially. Another one is a backward difference formula, fx minus delta over delta. Another one is a central difference, which is higher order, so you get order delta squared, and that requires fx plus delta minus fx minus delta over 2 delta. And all of those are legitimate approximations to the first derivative, and delta can be chosen arbitrarily. I'll give you a hint later on how to choose it, but you can choose an infinitesimally small number, maybe 10 to the minus 5, for example, as you numerically compute these derivatives. Now, you have an activity, and what are the advantages, disadvantages of each of these approaches? So notice some of them are first order, some of them are second order, but there's another caveat in there. So can you think of a few advantages and disadvantages for using these derivatives, numerical derivatives? Pause the video here, take a minute and think about this. So obviously, first order methods are cheaper to compute because you have less function evaluations. If you think about this, we had already, when we apply these formulas to Newton's method, we had already evaluated f of x, so we can save that. However, we need one more evaluation, f of x plus delta. And typically, a function evaluation programmatically requires the code to go to that function location in memory and then call it and evaluate it and come back, and that's costly. Every time you do a function evaluation, it is costly. So compared to the second order method, first order methods have one less function evaluation, which is highly advantageous if you're calling Newton's method billions of times, right? However, the advantage of the second order method is that it is second order, higher order accurate. However, you could argue that we're already doing an approximation in Newton's method, and the method we can probably get away with using a first order approximation for the derivative. We just shrink, make sure delta is very small. Anyway, I typically use a first order forward difference, so this first guy over here. And one hint for choosing delta is, you can put an infinitesimally small number, or if x0 is very large, you can just rescale that x0 by 4 or 5 orders of magnitude, and then also add a small epsilon, just in case your initial guess is 0. You don't want your delta to be 0. Okay, and this is what I typically use in my code, and this is an updated Newton routine that uses numerical derivatives, and I call this Newton 2. And you notice we dropped one argument, and that was df compared to the previous Newton routine. In this case, we only need the function f, an initial guess, and a tolerance number, and then we write this code, and notice how we compute the derivative on the spot over here. We say df is f at x naught plus h minus f at x naught over h, and then we proceed as usual. Now, go back to your Jupyter notebooks and use this code, which is already put in your Jupyter notebook. I highly recommend you go through these codes and learn what's being done, play around with them, run them for different cases, and see what happens. Okay, so I'm going to switch to the Jupyter notebook, and this is activity number 5. And notice how I have all of this already programmed for you. So here I used a reduction by 5 orders of magnitude of x naught. It's not a big deal. And then we can run Newton 2 now for, let's do u0 equal 40, or stay with u0 equal 10. u0 equal 10 meters per second. Let's do 40 first. And then we call Newton 2 on the residual function with an initial guess of 10 and tolerance of 10 to the minus 5. And we got the root at 15. The number of iterations is comparable to the analytical derivative, except it took us less work because we didn't have to program the analytical derivative. And then if we choose a u0 of 10, we expect a root at 68.66 for a drag coefficient of 68.7. Okay? Now, one last point on the secant method and Newton's method. Earlier, I alluded to the fact that the secant method gets stuck in minima, but we didn't kind of dwell on this a lot because we were going to address it in Newton's method. However, both the secant method and Newton's method, pretty much all open domain methods, they can get stuck in local minima. And take, for example, this function over here, x cubed plus 5x squared plus 2, and it looks like this. Now, I want you to take a minute, and if you start with an initial guess at x equal minus 2, so over here, right over here, x equal minus 2, start with an initial guess there. Graphically, think about how Newton's method, if we apply Newton's method, what happens to the prediction of the root. So in other words, take this initial guess, draw the derivative line, intersect with the x-axis, get the new guess, and then draw another derivative, and do it a few times, and try to predict what happens over here. Take a minute, pause the video, and take a minute. Okay, so I tell you that the estimation of the root, the method is going to get stuck. Why? Because if you start at minus 2, you draw a line, it's going to intersect the x-axis around maybe minus 0.7. And then you draw the derivative there, is going to drive you to about 0.1. Then you draw the derivative there, is going to drive you back to about minus 0.1, and you're going to keep oscillating in this little dip over here. Let me show you a Python demo that shows this. Okay, so what I have here is a Python demo that I am gonna run for you. So let's hide this. Okay, so this is a Python demo for this particular function, and I'm starting over here with a guess for the root at minus 2. So this is my guess, x0 over here in blue, and my new estimate for the root is this point in red. So we draw the straight line, intersects the x-axis. This is going to be our new guess over here. Now we do a second evaluation. The next step is going to take a derivative over here and intersect it with the x-axis. So we do this. Now we get to this point. Now do it again. And it's going to bring us back over here. Do it again. It's going to bring you over here. Do it again. Do it again. You see how you get stuck in this little in this local minimum, and that's always an issue for the secant method and for Newton's method. What you can do is you have to actually pick another initial guess. Okay, so if I change my initial guess to say maybe minus 1, or actually minus 3, let's see what happens if we go to minus 3. Okay. Go to minus 3 now. Okay, so that's the initial guess over here. Let me find the iterate window. Okay. Our initial guess is in blue. This is our new guess. Then it continues, draws a derivative, derivative. Well, it's gonna get stuck again over here. So, okay, actually we got lucky, and then we found the root. This is the root over here. See how we converged very, very quickly to the root. Okay, so we're not gonna make we're not gonna get any better from here.